Now, a couple of cases of this we've already seen. So let's start with the assumption that you've got just a single non-zero vector in R2, and you just take the span of that one vector. What you're going to get is a line through the origin. Now, in this case, it would be a line through the origin in the xy plane or the Cartesian plane, right? Because we took a vector u that's in R squared. But there's nothing stopping you from doing the same thing. Just take a non-zero vector in R3 and then take the span of that single vector. And what you'd get is you'd still get a line through the origin. It would just be a line through the origin that takes place in three-dimensional space rather than two-dimensional space. But in either case, the line itself is actually a one-dimensional subspace, either of R2 or R3, depending on which case you're dealing with. But this was actually discussed a little in more detail in section 1.3, along with a diagram and a picture. So I'll encourage you to refer to that if you've forgotten or if you want to maybe think it might be useful to revisit that. I'd refer you back to your notes in section 1.3 where that was discussed a little bit more. And same with the next example, part B. If you take two vectors, and in this case it really makes sense to do it in R3. You wouldn't do this in R2. But you could do it in R2, but it wouldn't be as interesting. So if you take two vectors in R3, and specifically two vectors that are both non-zero and linearly independent, so neither of them is a multiple of the other, well, then what do you get if you take the span of those two vectors? Well, in that case, you end up getting a plane through the origin, and that's an example of a two-dimensional subspace, because planes are two-dimensional. So those are just a couple of examples, and like I said, we've looked at those in a bit more detail in section 1.3, but not section C, part C here is new. This is a brand new set to consider. And you can see by the way I've written this down is this is actually an example of a set of vectors that fails to be a subspace. Let's take a look at why. So first of all, what's the definition of the set? Well, it looks like it's the set of all two-dimensional vectors. So the set of all two-dimensional vectors of the form xy, but they have to satisfy the equation, and actually it's not an equation, it's an inequality. X squared plus y squared is less than or equal to 1. So the way when you read sets that are written in this form, this is called set builder notation. So this describes a typical form that an element of the set must take to even be a candidate for consideration. And then this is a condition that must be satisfied finally to determine whether or not the object is in the set. So the objects are two-dimensional vectors, and the only ones that are allowed to be in the set are the ones whose coordinates satisfy this inequality. So what do you get if you look at that set? You can see here it's called the unit disk. And here's the reason. If you start with just the unit circle, and I'll do that in blue here. See how well this turns out. That's not bad, actually. This is actually, where should I write this? I'll write it over here. The equation of that circle is actually x squared plus y squared equals 1. So if you think of those points as vectors, the points on that circle, they're the vectors x, y that satisfy the equation x squared plus y squared is equal to 1. But you can see here we've got an inequality that is less than or equal to 1. So what's going to happen? The modification that that's going to make is we're actually going to also include all the points inside the circle as well. That's what the effect that inequality has. Okay, so we're not just including the points on the boundary of the circle, we're including all the points inside the circle. And that's why it's referred to as the unit disk instead of the unit circle. Oops, I erased too much here. There we go. Okay, so why is this not a subspace of R2? Well, what are the three conditions? Again, remember the first condition is that your subspace must contain the zero vector. Let's take a look at the zero vector. In this case, you're talking about, the only thing that would make sense is the two-dimensional zero vector, because we're talking about R2, and we're considering whether or not this set S is a subspace of R2. So in this case, the zero vector that we care about is the two-dimensional zero vector. And what you'll find is the zero vector is actually in S. And the reason is because you can just plug the two coordinates into this inequality and it'll be satisfied. If I plug 0 in for x and then 0 in for y, I'll get 0. And that's certainly less than or equal to 1. So actually the first condition of being a subspace is satisfied. It does satisfy one of the conditions. What about the second condition? Let's scroll up here actually. So it does actually contain the zero vector, but what about the second condition? Is it closed under addition? Meaning, is it possible to find two vectors that are in S, that are in the set S, and their sum is not in the set S? And actually, that's where you're going to see this does fail to be a subspace. One of the simplest ways to look at this would be just to take the standard basis vectors E1. Oops, that didn't look so good. The standard basis vectors E1 and E2. So that's E1 and that's E2. So what is E1 in terms of its coordinates? Well, it's 1, 0. Well, that's in S. And how do you know that? Well, use the same way to check, right? If I plug in 1 for X and a 0 for Y, I'll get 1 squared plus 0 squared is equal to 1. Is that less than or equal to 1? Yeah, barely, but it still is, right? And same with E2. E2 is 0, 1. That's also in S for the same reason, although the coordinates are flipped, but I'll have 0 squared plus 1 squared, which is exactly equal to 1, which is less than or equal to 1. But what happens if I add those two vectors together? And I'll draw it in the diagram. The parallelogram rule would say that this would be E1 plus E2, right? But that goes outside of the circle now. So it's not actually in the circle, that vector. Or let's look at it from an algebraic perspective. If I go E1 plus E2, well, if you add those together, you'll get the vector 1, 1. But now that is not in S. And the reason is just plug those values into the inequality and see if it's satisfied. Here you've got X is 1 and Y is 1. Plug those in. 1 squared plus 1 squared. That's going to be 1 plus 1, which is 2. But that's greater than 1. So this inequality is failed, or fails to be true. It's not satisfied, whatever you take your pick, for this vector when X and Y are both equal to 1. So for that reason, this vector is not in S. So property 2 fails. Here you've got two particular vectors that are in the set S, E1 and E2 in this case, but their sum is not in the set. So for that reason, we don't need to now go check property 3. Now we know condition 2 fails, so it doesn't matter whether property 3 is satisfied. This is not a subspace because if it were a subspace, it would satisfy all 3 conditions. So we can say, therefore, S is not a subspace of R2. It is a subset of R2, but not a subspace of R2. Okay, so there's another subspace we'll consider, and this one is it's the simplest subspace in the sense of being the smallest. It's actually a subspace of Rn. You always have it for any n, and I don't always emphasize this, but I will here. For any n greater than or equal to 1, you always have a subspace automatically. Just form the set that contains only one vector. It only contains the 0 vector. And that's always going to be a subspace of Rn, and it's referred to as the trivial subspace of Rn. So why is that? Why does it work? Well, remember what the 3 conditions are. Let's scroll up. The first condition of a subspace is that it's got to contain the 0 vector. Well, it certainly satisfies that because it only contains the 0 vector, right? So let's just write out the check here. So condition 1, the 0 vector is in H. And how do you know? Because it's literally written out that way, right? H is the set containing the 0 vector. So there's no argument that we need to give or no equations to check. It's simply there by the fact that it's listed as the only entry or the only element of H. Okay, so that's the first condition. What about the second condition? It says that, well, if you take any 2 vectors in the set and you add them up, the result had better also be in the set. Okay, well, we don't even have 2 vectors, do we? We only have 1 vector. So the only way you could take 2 vectors from H and add them up is if both of the vectors were the 0 vector. And that's, in fact, the only thing that you need to check. So if I take the 0 vector and I add it to the 0 vector, because that's the only way I could form a sum of 2 vectors in H, if I add those 2 vectors up, I'm going to get the 0 vector. And guess what? That's also in H. So that takes care of the first condition and the second condition. The third condition, remember, says that if I take any vector in H and any scalar k, and I multiply the vector by the scalar, the result had better be in H again. Well, the only option you have for your vector x is the zero vector, since H only contains the zero vector. But the scalar k could be anything. So let's say let k be a real number. Then what are we going to check? Just check that k times the zero vector. Well, what do you get if you multiply the zero vector by any scalar? You're just going to get the zero vector again. And hey, guess what? That's in H. So that takes care of property 3. Okay, so this subset containing just the zero vector, it satisfies condition 1 because it contains a zero vector. It's closed under addition, and it's closed under scalar multiplication. So it satisfies all 3 of the conditions. So we can say, therefore, H is a subspace of Rn. So that's a subspace that you always have, and it's called the trivial. Why is it called the trivial subspace? It's called the trivial subspace because it's so easy to check, in the sense that there's just not a lot of work to do to check. But also, it's trivial in the sense of it can sometimes just show up as a weird counterexample and it's not particularly exciting, right? It doesn't have any information in it. It's got only a single vector, so it's trivial. It doesn't have much depth or substance. That's where the name comes from. Okay, one last thing on this page is another subspace that you have always that can be determined by a matrix. So if you've got it, first of all, start with a matrix A, and let's say it's got dimensions m by n. So in particular, n is the number of columns of that matrix. So that's going to give you, right off the bat, that's going to give you a subspace of Rn. Now, what is that subspace of Rn going to be? How does it define a subspace? And what is a subspace called? Well, it's called the null space of the matrix A. Some books like to call it the solution space, by the way. Null space is more standard. But the definition is the null space of A. That's the notation, so just write the word null and then A in brackets. And the definition is as follows. So it's the set of all vectors in Rn, so the set of all x in Rn with the property, I guess we're usually using colons here, right? Yeah, I'll stick with that. I used a colon back here. Sometimes some books and contexts use a vertical line. I'll try not to interchange the two, so I'll stick with colons. So it's the set of all vectors x in Rn, and the property that they have to have is that if you multiply them on the left by the matrix A, you get the zero vector. In other words, another way to describe this just in ordinary language is the null space of A. It's the set of all solutions to the associated homogeneous system, right? Treat this as a matrix equation that happens to be for the associated homogeneous system, because that's your constant column is the zero vector. And the null space is the set of all vectors x that satisfy this equation. So you're talking about the set of all solutions to the associated homogeneous system.